Here I proclaim the beginning of the public oral defending of the dissertation entitled Prediktivno upravljanje u zgradama orijentirano na korisnike pomoću modela ugodnosti temeljenih na personaliziranim podacima. Human-centered predictive control in buildings using personalized comfort data-driven models. By the candidate Arlinda Bresa, Mag. Ing. Mech. The Faculty Council of the Faculty of Mechanical Engineering and Naval Architecture, University of Zagreb, based on the decision adopted on the second regular session of the Faculty Council held on 16 November 2021 and based on the decision of the Senate of University of Zagreb held on 21st May 2022, has issued a decision to initiate the process for obtaining the doctoral degree for the postgraduate student Arlinda Bresa, Mag. Ing. Mech. In addition, we were appointed as the committee members for the evaluation of the application for dissertation, of the doctoral thesis and the public defense of dissertation with the title above. The committee for the defense procedure has been nominated as follows. Full Professor Andrej Jokic, University of Zagreb, Faculty of Mechanical Engineering and Naval Architecture, Committee Chairman. Associate Professor Clayton Miller, Department of the Building Environment, National University of Singapore, Member. Professor Emeritus Dejan Ajdukovic, University of Zagreb, Faculty of Humanities and Social Sciences, Department of Psychology, Member. The committee has set the final defending of the dissertation on 30th September 2024. Please, you can sit now. I'll just read a short biography of the candidate. Arlinda Bresa was born in Unna, Germany in January 1994. She completed her education in her homeland, Republic of Kosovo, where she earned her bachelor's and master's degree in thermal energy and thermotechnics from the Faculty of Mechanical Engineering and at the University of Pristina. She graduated with honors for her outstanding academic performance. She conducted her doctoral research under the mentorship of Professor Tea Žakula within the Laboratory of Energy Efficiency at the Faculty of Mechanical Engineering and Naval Architecture, University of Zagreb. In addition to her doctoral studies, Arlinda has been a teaching assistant at the University of Pristina for the past 7 years. She has published several papers in high-impact journals and conferences. Her research and professional activities reflect her commitment to advancing the field of energy efficiency and sustainable building technologies. I will now kindly ask Arlinda to present her work in time up to 15 minutes. Arlinda, the floor is yours.
Okay, thanks everyone for being here today. I'm excited to talk about my research that I've been working on for several years now. And I will try to convey the enthusiasm that I had during these years with working on this topic, and I hope you will enjoy this presentation as well. So my research is regarding human-centered predictive control in buildings using personalized comfort data-driven models. First, I would like to thank my committee for being here today and my mentor, Professor Thea, Professor Andrej, Professor Dean, and Professor Clayton for coming here today. So I'm going to start with a question that I think all of us can relate to Sarah here, where we at some point have found ourselves being uncomfortable with the indoor conditions. So we were unsatisfied, and in some cases we even did not have the possibility to change the temperature setting or the indoor settings. And we are not alone in this, because 38% of occupants, based on a study made in more than 600 buildings, where 62,000 people were surveyed, said that they are uncomfortable or dissatisfied with the indoor conditions. Just to bring into comparison, what it means is that according to standards, for a building to be operating well, it needs to satisfy at least 80% of its occupants. And in another study done with more than 200 people, only 11% of those buildings, for more than 200, achieved this 80% threshold. So the thing is that these studies were done in states like US, Canada, Finland, which means that they do not lack in technology or a proper control system or HVAC system, but sometimes higher automation or higher technology does not suffice to increase comfort or for people to be comfortable. So what we as engineers often forget is that buildings are actually built for users, and we should keep in mind and take into consideration the personal preferences of people, where some people simply prefer warmer ambience, some people prefer colder, and the usual root cause of this dissatisfaction with indoor environment is the individual comfort preferences and the lack of access to control. So that is what brought me to the first challenge that I wanted to tackle, is how to integrate the occupant preferences into the automated control system. So how to enable this access to control of people and how to account for individual preferences. This brought me to a concept of human-centered control, which is a control system that prioritizes occupants. Imagine this, so an occupant or a person in a building reports their feedback or their opinion preferences either through a smartphone application or through another gadget. It provides that information in the automated control system, which considers that kind of preference and regulates the building based on those preferences. So this kind of integration of the user in a building enables us to have better human-building interaction while still prioritizing comfort, well-being, and satisfaction of occupants. However, in current research, because this is not a new concept, so people are researching it, this part where people are supposed to provide information or share their preferences with a controller are often assumed. So researchers assume that people will actually take a phone, provide their feedback or information. But the thing is, what do people actually want when it comes to this kind of interaction with the controller? This brings me to the second challenge on how, what are occupant preferences regarding the control systems, and are they willing to interact with the controllers by providing data? When people are supposed to provide data, it can be tiresome, or it can be like a burden for them to kind of report their feedback. What if we can learn those preferences and have a model that represents you? Imagine this, so instead of providing information continuously, you provide for a certain amount of time until the model learns your preferences, and you can create like a comfort model or your avatar, like a digital twin for you, which can know or represent your comfort preferences. On the other side, when we speak of comfort, we often have this idea of thermal comfort, like temperature, but comfort entails different aspects as well, such as indoor air quality or the quality of air, and visual comfort. This brought me to another challenge when I saw in the literature that most research focusing on personalized comfort model deal with thermal comfort only. And the thing is how to develop comfort models that also include visual and indoor air quality aspects, so to have it as multiple comfort aspects. Another thing, when we establish this human-building interaction, we can leverage it in terms of, we know that occupants are a significant contributor to the energy consumption in buildings. So buildings take the energy from the grid, and at times when the grid is overloaded with energy, what if we can leverage this kind of connection to make a conscious decision on reducing the energy consumption when the grid is overloaded, or use the energy from the grid when it has more energy than needed when we use renewables. So this kind of interaction can be leveraged or used with human-centered control. And this brought me to the last challenge, is how to leverage this kind of interaction with occupants and control systems in buildings, and what is the impact of human-centered control in grid flexibility. The goal of my thesis here is to provide a framework where we can integrate occupant preferences into building control by using personalized comfort models to regulate the indoor conditions. The hypothesis of my thesis is that integrating user control or using human-centered control systems in buildings enables us to increase the satisfaction of occupants with indoor conditions. The contents include, I divided this research into 4 topics. The first one deals with the human side of human-centered control by eliciting occupant preferences and their willingness to interact. The second topic includes the development of personalized comfort models, where here I developed a method to have different comfort aspects for models. And the third one is the integration of user preferences into the building control system, where I provide a framework on how to integrate users into the controller. And the last topic that I tackle is to define and quantify the impact of human-centered control in grid flexibility, so how to interact with the grid. The first topic answers this research question is, what are occupant preferences regarding control systems? And can we predict the willingness or the intention of occupants to interact with this kind of controllers, either to regulate the indoor condition or to engage in grid flexibility action, so to make conscious decision based on information from the grid? The methods that I used here is a survey-based method with more than, around 1,000 people were surveyed in Zagreb in Croatia, in order to find insights on their preferences regarding control systems. The target group that I aimed at was mostly young people, because they are the most likely users of human-centered control, considering that the widespread application of this kind of control system is still in the development phase. And during this survey-based research, I tried to target a balanced demographics in terms of age, in terms of sex, and in terms of background or technical knowledge that they have. So not to have only people from the technical side, but also from the social side. And another method that I used is based on the behavioral science theory, which is a theory of planned behavior. Basically, what I did is I took an existing theory from the psychology department, and I applied it for control systems. For instance, this theory says that if someone has the intention to run, or is willing to run, they are more likely to exhibit that action. And also it depends on the kind of drivers or motivation, intrinsic motivation they have. So if they have a belief that it's beneficial, or their social circle is doing that, or it's easy to exhibit that action, they are more likely to do so. And I applied the same in the concept of human-centered control. So if someone says they are willing to share data or interact with a controller, they will be more likely to do so. For this, I developed a concept, like a framework, which has different influencing factors and to predict this willingness. So due to time constraints, I will not go into detail for this, but I have 3 papers that were published in this regards. And the results from this research showed that from almost 1,000 people surveyed, 47% want to have full automated control systems in buildings, whereas 27% want to have manual control. From those almost 1,000 people, 76% of people want to have access to control, but if we ask them, do you want to share data, only 55% want to interact by sharing data. So we have this willingness, yes, I want to have access to control, but they hesitate to share data with the controller. In terms of the interface, what they want to use is that 66% prefer to use smartphones, while 73% want to interact with these kind of controllers only when they are uncomfortable, and almost 30% want to receive notifications or reminders on reporting or sharing their data. So this is important to kind of make this reporting thing easier for the applicant. So it would be mindful to use these, to take into consideration these parts. At the same time, from the survey, I gained insight on which comfort aspect do people actually think it's more important to them, and I saw that the majority find indoor air quality to be the most important, followed by thermal comfort and visual comfort. So although the research mainly focused on thermal comfort, we see that indoor air quality is the most important to people, and this might be changed in the post-pandemic era, where indoor air quality gained more focus. Also from the survey, I found information on the occupant preferences regarding grid flexibility interaction, where according to the survey, 60% of people are willing to interact in this kind of programs or actions. However, 48% only want to interact for 1 or 2 hours, so for a short period of time only. And regarding the monetary incentives or financial benefits, 31% would interact with the grid even with no financial gains. However, 20 and 27% would like to interact with small or moderate gains, and only 7% want to interact for only high financial gains. So if they gain much financial benefits from that, this shows that even like if you pay people more to interact with the grid, they are not more willing to interact. So this shows that yes, a part of financial gain is important, but not that much. In terms of predicting the willingness, the framework that I used showed a 64% accuracy, meaning that I can know with a 64% certainty that if a group of people will report feedback or not, based on this framework that I developed. And the highest motivator were the thought or the belief if this kind of control system is beneficial, how easy it is to report, like to use either a smartphone or this interface to report feedback, and the social impact if other people use it, as well as user trust. So the takeaways from this part is that regarding the preferences, people want to have access to control, but they hesitate to share data, and their preferred user interface is a smartphone. In terms of comfort, we saw that indoor air quality is the most important comfort aspect. And in terms of grid flexibility, people have the willingness to interact, but only for a short period of time. And also for incentives, higher financial gains does not mean higher engagement of people. And the willingness, so we can predict with a moderate prediction accuracy if people want to interact with a controller or not. So this brings me to the second part of my research, is the development of personalized comfort models, where I answer the research question on how can we develop personalized comfort models for multiple comfort aspects and for multiple people, and how can the data be effectively collected, and how to develop a data-driven personalized comfort model, and how much data is needed, and which is the most reliable machine learning model to do so. So first, I'm going to start with like a big picture on how does human-centered control, which employs personalized comfort models, work. So imagine this, we measure indoor data with sensors, and at the same time we ask you to report feedback on how you are feeling in terms of is it too hot, too cold, or too bright, too dim, so you can report your comfort level. And for instance, if Sarah here says that she's cold, then I collect this information and I developed personalized machine learning models which learn based on your historical provided data and can predict in the future how you would feel. This kind of comfort models are linked or connected to the control system of a building, which enable this integration. And then after some time, you will not need to provide information anymore, but the personalized comfort model will know your preferences. So the methods that I used for this is I executed 2 experiments. The first one was a laboratory experiment where I collected data and I developed the personalized comfort models. The second is a field experiment where, again, I collected data, I tested the outcomes of the first experiment, and I integrated this human-centered control concept in an actual building. And also I employed machine learning models here to develop and compare different machine learning models. So in the first experiment was done in a laboratory, and here are the participants, where 4 of them participated in the experiment. So it was in an office for 3 weeks with 4 participants. Here we measured indoor parameters such as temperature, air humidity, CO2 levels, and lighting level. And at the same time, they reported their subjective preferences and sensations. And I managed to collect different data points, up to 198 data points per person. How I collected the subjective feedback is that, if you remember from the first part of my research, 66% of the users wanted to use a smartphone. So I developed a simple smartphone application, which is a survey-based application where you can answer some questions in order to provide information on how you are feeling. I called it the Age Comfort app, and this can be used to report data, and the data collected from here goes directly to update the personalized comfort models. So a personalized comfort model looks like this. So here we have the inputs, which are the objective measurements, say air temperature, air velocity, relative humidity. And we have the subjective measurements as well, such as thermal sensation preferences, air humidity sensation, air movement preferences. So these inputs were inspired from existing research, and I tested on what happens if I remove some of them, but I will not go into details for those today. And if we get these inputs together, and you at some point give me the information that you are comfortable or uncomfortable, so it learns based on this, and I did the same for indoor air quality and visual comfort as well. So this kind of setup where you have the inputs and you know the outputs for some time is called, can be used as a supervised machine learning model. And this is the classification model because it can predict either comfortable or uncomfortable. So for instance, if you have a setup of indoor parameters, and today you say that you are uncomfortable for these conditions, tomorrow after a while for the same parameters, it can predict that you are uncomfortable. The results from this part is that first, during the lab experiment, I saw that the comfort profile of the participants differ from one another. So this shows the variability on perceived comfort. And if we compare it to current standard, for instance, in the UK, they say that for offices you have to have 20 degrees Celsius. We can see that it will be outside the comfort boundary of all of my participants. However, if we use other standards such as ASHRAE, then it lies within, but it depends on what the building operator chooses to use within that boundary. And here we see that for the lab experiment, this is the comfort zone where all of my people would feel comfortable. And that is why it's important to include occupant preferences into the control. So, which machine learning is the best when developing PCM? So I developed these personalized comfort models for all of my participants. However, I did not know what model to use, so I tested different, which were most used in literature. I tested 9 different machine learning models for all 3 comfort aspects, and I saw that for all participants and all comfort aspects, random forest and decision tree were the best performing ones, with an F1 score, which shows the prediction potential of the model, of 87% and 86%, which aligns with existing literature, and it shows that even if you have different preferences of people and different comfort aspects, it can be predicted with a very good accuracy. And also I wanted to see how many data points are needed to develop this model. So how many times do you need to report your feedback for the system to learn it? And I saw that at around 50 to 60 data points, or if we translate it for 3 times daily, you need 20 days of 3 times daily amount of data to develop these models. However, the number of data is not the only thing that we need. We also need to have variation or variability. Here, for instance, in the lab experiment, for different days, I had different air temperatures where I kind of tested the comfort boundaries of my participants just so that I learned how they react at 26 degrees, for example, and how they react at 20 or 90 degrees. So I kind of switched things up during the days, and also in terms of indoor CO2 levels, we had different variation of the data, and this variability is important to make more robust and stable comfort models. All these findings that I had in the lab experiment, I also tested in the field experiment in a school building or a living laboratory that we had here, the Ruđer Bošković High School building, where I had 24 participants for 1 week in one classroom. I did the same measurements, like the temperature, air humidity, and so, as well as the subjective feedback from the occupants. And however, here I had less control over the participants, so they were able to report whenever they feel like it, even if we nudge them to report feedback. However, I had less data than the lab experiment and different feedback behavior of the participants. So here again, I tested which machine model can I use if I have so little data, and I tested again the 9 different machine learning models, and I saw that decision trees work relatively well, even for less data, and for different engagement types. So even I had some people with very small number of data provided, this decision tree worked well. So the takeaway from this is that regarding the set points, occupant preferences does not always comply with the standards that we have in buildings. The best models are these tree-based models or decision trees and random forest. Decision trees is particularly good when we have less data available, and we need at least 50 to 60 data points with variability to create stable personalized comfort models. And if possible, it is good to have this kind of intervention days where you can make on purpose people feel uncomfortable just to know their comfort boundaries. Okay, this brings me to the third research topic that I had, is the integration of user preferences into building control. So here we had a kind of a hands-on approach in a real building on integrating user preferences into a controller, and we saw firsthand on what is the user experience, how do people actually perceive or experience this kind of interaction with the building. So if we have different people in a room with different temperature range which they are comfortable in, how to accommodate the different preferences of different people. So we tested this in an actual building, like the school building, the field experiment, again, like in the same time for 2 weeks with 24 participants, where during these two weeks I used 7 working days for learning their preferences. Once I learned, I developed the personalized comfort models, and I used 3 days for testing. So these days for testing were to adjust the building based on the comfort ranges of the occupants. So what I did is for one person, I developed their indoor air quality comfort model, thermal comfort model, and visual comfort model. However, in the building, here I'm going to show only the temperature. I did not integrate the visual part because we could not due to the constraints in the control system. And the CO2 level was not needed because the preferences of the occupants were the same, more or less the same with the standards. However, the different part was the temperature. That is why here I'm focusing only on temperature. And I developed the models, and I saw the profile, the comfort profile of the occupants, and I took a standard deviation with 95% confidence interval, which satisfies most of the occupants. So again, even if I have a different group of people, their comfort kind of overlapped with one another, and from the field experiment, this was the comfort range where most of my participants were comfortable, and this was integrated into the building. So if I took this comfort range and I tested it for 3 days, I saw that before the integration, so the participants were not informed which days we are including their preferences and which days not. But before integration, when asked, 40.5% were satisfied, and after the integration days with similar outdoor conditions, I achieved 57.2% satisfaction. So a 60.7% increase and a 15% decrease in dissatisfaction. This supported my hypothesis that implementing human-centered control actually increases the satisfaction of occupants. And now, if we have this 50% dissatisfied people, we kind of made our building go into that 11% of buildings that satisfy the ASHRAE standard. And in content, what does it mean to have 50% decrease in dissatisfaction? Is that from the first study where I had, where they surveyed 62,000 people, if we managed to kind of make 15% of those group feel better or be more satisfied, it would mean that we would have 9,300 people more satisfied, which to me is kind of a significant impact. During this experiment, we also had an like semi-structured interview with the participants, where we saw that interacting with the controller is easy, so they did not find it that much burdensome. They required to have less feedback because we were asking, since we had 2 weeks for frequent, and they wanted less. And still some said that they would use this in the future. However, they want to have the possibility to adjust the controllers manually. So the takeaways from this is that we can integrate PCM. So we tested it in a proof of concept in a real building, which satisfies most of the people, and we have an increase in satisfaction for 16%. And regarding the experience, we saw that people or participants actually took it well, this kind of interaction. And this brings me to the last part of my research, which is the impact of human-centered control on grid flexibility, is how can human-centered control affect grid flexibility, costs, and comfort. If nowadays the electricity grid has a lot of renewables and also the increasing demand in energy consumption. So we have grid power loads and fluctuating electricity prices, as we can see in real data from Denmark energy grid. So here the red line is for January and the blue line is for August. And you can see how it varies for different hours during the day. If we can leverage control system and humans in a building, then if we inform the occupant that the grid is overloaded, for instance, here we take Sarah and her comfort boundary. So if she accepts less comfortable condition, which means meaning she will reduce energy consumption, then this would lead to a reduction in energy consumption, which will enable grid flexibility. I tested this by using simulations with 2 control systems. The first one is a PID control, which is the traditional control system which is used in most buildings. And then we have an advanced control system which uses prediction and is not that much deployed in buildings. I tested them for standard set points, human-centered or desired set points were 21.8 based on the field experiment. And the last scenario is using the same standard set point, but engaging the occupant in reducing energy consumption with the grid. So engaging in grid flexibility action. The programs were used Transys and Method. This part of the research was done in collaboration with another PhD student. So it's a joint effort. And here is the results. We have the performance of different control strategies. I tested different scenarios, but here I will present only 2 of them. This is how the building operates with PID control, with standard temperature for a day during the summer. And in the x-axis is the time of the day. The gray part is when the grid is overloaded or during the peak hours. What happens with the energy consumption is that it's quite high, and also high during the peak hours, when this blue line is the electricity price, when the electricity price is higher. So if we employ the part where we use this modern control system, model predictive control, and we engage occupants in grid flexibility, then we see this change. The green line is when we use grid flexibility engagement and human-centered control with model predictive control. And what happens to the energy consumption is that it significantly is reduced, especially during the peak hours, because this kind of control system enable the load shifting. So it uses energy here where the electricity price is lower, and then reduces the energy consumption when the electricity price is higher. If we talk in number what it means, so this grid flexibility using model predictive control, this advanced controller, and human preferences enables us to shift the energy for 21% during the peak hours to off-peak hours, so during winter. And during summer, we have an 88%, because during winter, people prefer it warmer, which causes more electricity, so you cannot shift that much, but during summer, it enables a lot of shifting. Regarding electric energy costs, if we integrate occupant preferences into this traditional PID control, we have more than 200% increase in cost, which is terrible. But during summer, we can achieve some cost savings. And if we use this novel control, we have during winter 4.6%, which is not much, but still positive. And during summer, we have 97.8%. And regarding comfort, we can compare it here that if we use standard PID and grid flexibility, although you are kind of not forced but agree to use less comfortable conditions, you will still be more comfortable than if we use standard PID. During winter and during summer, you will be a bit more uncomfortable during those 2 hours. However, it will be with your, so you will agree to that. And this comes to the ending that the takeaway from here is that if we use grid flexibility with human-centered control and MPC, we have high load shifting ability of the building. However, if we use human-centered control where we take into consideration occupant preferences with traditional PID control, it will cause a lot of energy consumption and higher costs during peak hours. And the third part is that we have some discomfort, but it's agreed upon. So you willingly are accepting less comfortable conditions. So in conclusion, I presented work on providing a framework to predict the willingness of occupants to interact with human-centered control and their insight on preferences. This is useful because if someone wants to develop human-centered control, they can always go back to my findings and to design their human-centered control based on actual user preferences. And I also provided a method to develop multiple comfort models for multiple people, which shows that this is important because the framework I have, the application and how the data flows, I can create models for any occupant in any buildings. And also the framework to integrate human-centered control into a predictive controller is a proof of concept study, which was actually deployed, and it can serve as an example on how to do that, and the definition and quantification of the impact of human-centered control in grid flexibility, showing that the potential that we can have when integrating users. Okay, so it has been a long talk, but in conclusion, what we have to keep in mind is that the goal is that we need to prioritize occupants in buildings, and when we create human-centered control using personalized data-driven model based on evidence I provided, we can increase the satisfaction and comfort of occupants. If we use human-centered control and combine it with model predictive control, we can empower people and buildings to be more responsive, like to contribute to grid stability. And also this combination, human-centered control with model like advanced controllers, can enable more energy efficient and more sustainable future while still always prioritizing the users. So we saw that yes, this is possible, we can prioritize occupant preferences, but only and better if combined with advanced controllers and with grid flexibility actions. So in future it would be interesting to see the deployment of this kind of controller that was developed in other buildings as well. So here is a list of publications that I achieved during this PhD, which some of them might explore the research that I talked about. And I would like to thank my mentor, Professor Thea, and also the PhD members for listening and for all their advice throughout these years. Also, I would like to thank the Laboratory for Energy Efficiency, which are also here today, Nicola, Borut, Franco, Lucia, and Ružica. And also I would like to thank my family. So this is the only picture we were all together here. So it's a bit fancy, but anyways. And also I would like to mention that this thesis was done in loving memory of my fellow PhD colleague, which unfortunately she passed away. However, I would like to have her here today as well. And so I am done, and you can, if you have any questions, we can solve questions. questions.
Thank you, Arlinda, very much. Thank you very much. As you mentioned, now it's time for questions. And I would first like to invite Professor Emeritus Dan Idukovic to ask his questions.
Yeah, thank you. First of all, thank you for a very